Okay, so the final module to conclude FDTD is, we have spoken about everything except how to deal with sources, right? If you give me a current source or an incident field, how do I actually get this into the equation, right? So that's the sort of final module here in FDTD, right? And it turns out that there are two different classes of problems that we have to worry about, okay? It's almost like two different research communities. One is like the antenna community, where you specify the current source. You say here is a current source, this much value, so many amps is there at this place in time and space, okay? And the second one are the people who do scattering problems. So when I am calculating the radiation cross section, the radar cross section of an aircraft, the illuminating antenna is so far away that I am not going to incorporate it in my simulation domain. All I know is that there is an incident field, right? So these are two different approaches, and we will talk about how to handle both of them for FDTD, okay. So we will deal with the current sources first, right. So this is the easy part, right. This is coming straight out of Maxwell's equations, okay. So a volume current excitation is simply given by the term that we all know, J at some point in space and time. Okay. So for example, if I take the TE case, right, 2D TE case. So TE case, what are my variables? No, EX, EY, HZ, okay. It's always confusing, right. So let's write down what the stencil looks like. This is my EX, this is my EY, and my HZ is at the center over here, okay. And what was our update equation? I had curl of H n minus half, we've just recently written this, so we can just write it down, epsilon E dot n minus half, and I had a plus j n minus. Okay. So in terms of, if I take the components over here, what happens? So this is a vector, remember, these are all vectors, right. So how would you implement it? So we need to know J, which is my Jx and Jy, okay, if there is a Jz also, but Jz will actually go into the other polarization. Let us leave it for now. So if I know this as function of R and T, then wherever my update equations are, I just simply add this value of J, okay. What is the most natural place in natural position in space and time where I should add this or incorporate this into the update equations? Along with J actually, sorry, along with H. Yeah. So I mean, first of all, we should know it at half integer time instance, right? But if you give me J as a function of space and time, then wherever it appears, I just substitute it, right? So but you are right. So this is at time instances n minus half, but you are right that at the space location is going to be the electric field, because here when I have a space derivative of magnetic field, I am going to get those finite differences, right. So Hz from here minus Hz minus here, or left and right, whatever. So it is going to be more accurate at the E field locations, right, at space instances yeah, electric field derivative at n minus half captures everything, right. So this is nothing very difficult over here. Okay. Now it seems that that's all there is to it. Just put in the value of J and you are done, okay. Now the question, interesting question is there going to be any constraint on this J? So in our FDTD simulation, let's for now forget PML and all that, right? What are the parameters that you have to set to run your simulation correctly and get the correct answer? What do you have to decide before you run the simulation? Courant stability factor, right? So I have to set delta x, delta t and alpha, right? Alpha should be such that it is stable, right? This is what I have to set. Now the question is there any relation between how fast a J or any relation between the current term and these parameters, or does not look like? Should not have frequency components, right? Very good, right. So is there a relation between the current source and delta t, delta x, right? So your J, let us just take it as a function of time, right, will have some Fourier transform, right. So if I write down the Fourier transform over here, it will have some J tilde of f, okay. And let us say that it is band limited, okay. Let us say it allows only a maximum frequency variation up to some number, right. So it is, say it is band limited. So J tilde f is equal to 0, f greater than f naught. So f naught is the maximum frequency. Then by the Nyquist theorem, right, in order to correctly represent this Jt, is there a constraint on the time samples? Yes, right. So what should the time sampling be? Right. So delta t is there and twice, right. So that is going to be 1 by 2 f naught. Now this delta t should be greater than or less than this? Less than this, right. I have to sample at least the Nyquist rate in order to correctly represent this thing over here, okay. And at the same time, we have our Courant factor, right. So Courant factor, what does it say? Alpha is equal to C delta t by delta x, right. This is bounded depending on the dimensionality, 1, root 2, root 3, whatever, right. So given a current source, I get a limit on delta t, that delta t cannot be any greater than 1 by 2 f naught, then so your delta t is fixed. Now you have also got fixed your alpha, right. So therefore your space step is also fixed, right. So f naught fixed implies delta t fixed implies delta x fixed, right, because in FDTD space and time are very strongly related, you cannot independently do whatever you want, right. So if I have a very high bandwidth current source, right, so the implication is this, that if I have a very high bandwidth current source, space discretization must be very fine, right. It sounds like what is the relation, but you can see the relation is via the Courant parameter, right. Space discretization so you have to do this calculation beforehand, because once you have coded up your update equations, your alpha is fixed. So the moment you give me delta t, my delta x is fixed, right. Now if I go in and change my current source and make it to have higher bandwidth, what will happen? All your update equations will run, stability will be there because you have fixed alpha correctly, you will get some answer and that answer will be wrong, because your current source only is not being implemented correctly, right. There is not enough resolution in the time step there to capture the full characteristics of the current source, right. It will capture a band limited version, alias version, right. Yeah. So all these kinds of things will happen and it will be very hard for you to debug what exactly happened because you skipped signals and systems. So, this is a very important aspect in your setting these parameters correctly. So, let's take an example, okay, a popular kind of implementation of a current source, okay. So, you use a Gaussian current source is very popular, okay. So, for example, it is a Gaussian, forget the space dependence. Okay. So, by controlling this TW, I can make I can play around with how sharply the current sources are, right. So, typically supposing you wanted to implement a current source which was on at just some particular time instance. If you implement it as a step function, what is the problem? Supposing there is a on off, I mean there is a current source you want to implement and you implemented it as a delta function, okay, or as a step function, 0 for so much time, then on and then 0. What will happen? The frequency components are so large that I mean what we just saw previously, my f naught becomes very large. So, instead of doing that, I implemented in a smooth way. So, the Fourier transform of this is, Fourier transform of a Gaussian is a Gaussian. That is one of the reasons you choose a Gaussian way to implement a source, right. So, I will just write down the Fourier transform. This is in the frequency domain, okay. So, which of these terms is giving me the sort of 3 dB bandwidth? I mean, how do I know the width in the frequency domain? Which term is going to, or what is the width? What is the bandwidth roughly? Right. So, it is going to be 1 by pi TW. Right. After that, it begins to drop off in amplitude. That is what we are looking at. Right. There is a carrier frequency over there also. Because at 1 by pi TW, what happens to the value of this exponent? It drops by 1 by E, right. That is how we define bandwidth roughly, right. So, that is so what we can do is, to be on the safe side, we can set f naught, the maximum frequency, maybe 2f BW, right. So, if I filter this signal in frequency domain at 2f BW, I have captured most of the signal, right. That is a safe safeguard, okay. So, that implies that f max, so this f naught is equal to my f max, that is equal to 2 by pi TW, okay. So, this is my maximum frequency and this fixes indirectly, this fixes delta x, right, just as we did over here. Once I fix my f naught, I get my delta t, I use the Courant parameter to fix delta x, okay. So, this is just an example. It is a very popular way of modeling a current source, that is the reason we are doing it, okay. So, you can control how many frequencies are in this in your current source by playing around with TW, right. You can implement a very broadband source or you can implement a narrow band source by playing around with this TW, right, because narrow in time is wide in frequency and vice versa. So, so it is very, very popular, right. You will not want to implement it via a step function, you will use something like this, okay. So, this is showing you how to sort of the issues that you have to keep in mind, right. So, in other words, to fix your delta x, you need to keep an eye on this TW parameter, that is the implication over here. So, this was one. Another aspect is what happens when you start the simulation, right. So, at the start, that is t is equal to 0. So, what is my g of 0? E to the minus t naught by t w. So, again here is a factor. Suppose your simulation starts and at time t is equal to 0, suddenly you have a very large value of current, right. That is a source for a lot of numerical instability, and this will give rise to higher frequency components, right, because as far as the simulation is concerned, at t is equal to 0, let us say you set everything to 0, the next time instant delta t, suddenly you are setting g0 to be so high, right. So, this in turn may give rise to higher frequency components, right. So, what is the fix for this? If you wanted to minimize, if you want to minimize high values of G0, simplest fix is increase TW, right. So, make TW large, right. So, example, so TW is going to be fixed, so not TW, T naught, right. So, T naught for example, I can fix to be say 4 TW. I do not want to play with TW for this. TW is what is controlling the characteristics of my source, narrow band, wide or wide band or whatever. But T naught, supposing I fix to 4 times TW, then what happens is this is e to the minus 16, which is a very low number. So, my simulation starts very gradually, right. I do not encounter very high frequency numbers or whatever, right. What is the price I am paying? There has to be a price by doing this. Discretization is, how does that change with T naught? Discretization is fixed the moment I fix TW. What is the price that I am paying by setting T naught equal to this? My simulation time has increased. I have to start all the way from when the source is very low in value. I could not have started just at the peak. I have to go back to the tail of the Gaussian, wait for it to build up, then I get a smooth frequency distribution, everything, right. So, the price is longer simulations. Okay. And the final sort of thing to keep in mind is, we have not spoken about how long to run the simulation for, right. How long should it be? Yeah, so similarly you should go for an equal amount on the other side of your T naught, right. So, you could go from, so 4 times, we said 4 TW before the pulse maxima and another 4 TW after the pulse maxima, right. So, answer is long enough. Example 4 TW into 2. So, a common mistake could be, right. So, a common mistake to avoid is, example, I set the total time equal to, let us say 2 TW, right. It's everything is coded up, your time step is correct, space step is correct, everything is correct, but you forgot to run the simulation for long enough. So, you just simulated some very small part of the pulse and you have not because those frequencies were not generated, you have not actually been able to study your problem properly, right. So, these are all the further aspects that you have to keep in mind after you have coded up perfectly, right. So, even a perfectly working code may give you wrong answers if you do not, for example, fix your T naught correctly or capital T correctly, okay, which the simulation will not tell you. Simulation will give you some numbers, okay. So, there is a lot of research that has been done into how to define the current source as a function of time, which I am not going into, but a lot of work has been done, and this software which I have mentioned to you earlier, MEEP, has many different ways in which you can choose the current source best suited for your application. We'll come to it later. So, this is what would be called a hard source, right? Is it fine? Okay. So, we'll close it over.